we'll aim for 3 o'clock.
Okay. Thank you, Wendy. Oh, it's loud. Good afternoon, everybody, and welcome here. So the final session, at least on the presentation side, is going to look at continuing evolution of the IEC 61850 standard. In fact, you see my picture there. It says new gooses. How many here, out of curiosity, know what goose messaging is in 61850? Not that many. Interesting.
Well, he taught us this morning.
Yeah, we have. Nobody learned anything.
They obviously didn't listen to you, Alan.
I should kill myself.
Well, we're going to extend it anyway. So, to start with, you probably have seen this picture here. And this picture was where 61850 started out. Meaning, we looked at what devices in the utility enterprise. In fact, let me this one clarification here. When the first edition of 61850 was released, the focus was the utility substation. It quickly became apparent that 61850 had applications well outside of the substation. In fact, the name of the standard changed from Edition 1 to Edition 2, where in Edition 1 it was focused on substation communications. In Edition 2 it's focused on utility communications. So it is the one protocol that can encompass all the way from the meter on your house all the way up to the energy management system at the head end of your utility. Of interest here, however, is that this picture has not been static. Whereas this picture shows communication between relays, and you heard Steve before talk about process bus. What's been happening are the extensions. And a couple things. First of all, we have NERC, the North American Electric Reliability Corporation, has stated everything around a substation has to be secured. Any communications has to be secured. Anything that crosses what is known as the Electronic Security Perimeter, or ESP. And so we can draw this box around that substation or any communication facility in the utility enterprise. When a communication link crosses that boundary, it must be secured going forward now with NERC SIP. There are many utilities that interpret that even communications inside the substation have to be secured. This is an issue. I use the word interpret because NERC SIP is a bunch of guidelines, and then it's up to an auditor to interpret the guidelines and how they apply to a particular utility implementation. So it's unfortunate the way that they've done this, but it leaves it up to the auditors to decide whether or not a particular implementation is compliant or not with NERC SIP. What's been happening subsequently, though, is we see there are now new linkages coming out of the substation in the 61850 world. Specifically, we have from the station level to remote energy management systems and remote synchro phaser systems. In fact, right here in this Northern California region, Pacific Gas and Electric does use 61850 to communicate synchro phasers from the substation to multiple energy management facilities. So that is an extension of 61850. The other major extension is off to the left there, and we now see substation to substation communications. In fact, I'm going to go beyond this, and with all the distributed energy being installed in California, communications from the substation head end to all the distributed energy devices on a feeder must be secured now. Well, it's interesting, because this is in the gray area. And again, I'm not going to interpret this, but I'm sure that any utility putting in communications will secure that communications. I say it's a gray area because typically NERC critical infrastructure protection applies to what's called the bulk electric system, where there are major power flows. Distribution is not major power flows, but it can have an effect on the power into your home. And so the utility is not going to want to take a chance with leaving that out in the open. So these are two new areas where there have been extensions to the 61850 protocol, and I'd like to go into some description of these. What's happening also is all substations are having firewalls installed. A firewall is a mechanism that filters data going into and out of the substation. So devices like the Goose message that Alex talked about will not go through a firewall. The firewall kills the Goose message. So the question is, how do we get messaging through that firewall? So the drivers for change started on the synchrophaser world, where synchrophasers traversing outside the substation needed to be secured, and multicast. Multi is a key terminology here. Alex would have explained. With the Goose message on a local area network, it is multicast, which means the one device sends the message, many devices can receive that message. When we go out into the, I'll call it the wild world outside of the substation, I'm no longer on a local area network. I'm now on what is known as a wide area network. Wide area network is actually multiple local area networks connected with routers. So a messaging technology needs to be implemented that can go and span multiple routers in the electric utility enterprise. I like referring to it as the electron enterprise. Anywhere electrons flow, the control of those electrons need to be monitored and controlled. Going forward, it was critical to be able to configure what is known as a data set. I like to think of a data set as a shopping list. You go to the store, I want one of these and one of these and one of these. 61850 is founded on the ability to create these shopping lists of data items from a substation. There were no standard data names in the original synchrophaser standard. This was a very strong desire to have standardized names and name length. We'll go into that, but this was so the driver was the synchrophaser. The bonus was that, well, while we are making the synchrophaser message multicast, why not use the exact same process for making Goose messaging multicast? And that's exactly what has been done. In our world, as we develop communication protocols, they are typically developed to solve a problem. The problem in the utility world that was the driver, what we call the use case, was synchrophasers. And synchrophasers in this picture here shows I have multiple sources of this measurement data, and then multiple users of the same data. So we have a many-to-many communication problem. And this was the primary use case for the development of the routable Goose and what's called the routable synchrophasers. Today, as I'm sure Alex mentioned, when you have Goose in a substation. It operates only on a local area network. When you send a goose message into a router has no idea what to do with that goose message. As a result, that message winds up in the bit bucket. Literally gets thrown away by the router. What needed to be done was to change the messaging format of the goose to allow it to go through the router. And this has been done right now with by adding, you all know the Internet Protocol. What was done is a Internet Protocol address has now been appended to the goose message. This makes the goose message routable over an entire network. So, as an example, I can, and this is what's called a multicast message. If you've ever listened to internet radio, you know what a multicast message is. When you get on your computer and you tune in an internet radio station, you are listening to a multicast message. The one station is publishing the radio message, and many, many people are receiving that exact same message. That's called multicast. But notice the words I used. You have to tune in. You have to ask to receive that message. This is a key element of how the multicast goose is going to work in the utility environment. What we want to happen is for that message to be able to transit through the router or multiple routers in the utility environment. There is a technical report that's out, and the technical report is known as Part 90-5, which is use of IEC 61850 to transmit synchrophaser information according to the IEEE synchrophaser standard, which is C37.118. I was on the committee, and for me it was obvious what the new name of this should have been. It should have been the Networked Object-Oriented Substation Event, or the NOOS. People got hung up on the name. So, as a result, the official names of these new routable protocols are called RGoose for routable goose, and RSV for routable sample values. Again, I'm going to probably reiterate what Steve and Alex said, but I just want to clarify. Goose is sent on an event. Only when something happens is the goose message sent. So it's an event-based message. There is a keep alive, but I'm not going to go into that right now. The difference, though, is sample values are periodic. When I'm taking samples on a waveform, I have a certain sample rate at which those samples are taken. When I send synchrophasers, I have a certain rate at which the synchrophasers are reported. So sample values are periodic, goose messages are event-based. Clear distinction between those two message types. 61850 continues to evolve. In the beginning, this picture didn't look doesn't look like it does today. Specifically, what we see added in here are 3 new profiles. By the way, I'll define the term profile. A profile is a set of protocols in a line that perform a certain function. So, in the past, we had a profile for goose. We had an application layer that said, here is how the data is mapped into the message to communicate. And by the way, all the communications were over Ethernet. And that is the profile for for the original goose message. What we see new here in these new profiles I have highlighted here, you see that now for the routed sample values and for the routed goose, there is now a UDP IP layer. A UDP is what's called a transport layer. I'm trying to think of the acronym. UDP. Alex, Steve? User data profile. Yeah, thank you. User data protocol. IP, of course, is the Internet Protocol profile, though. So the IP is a layer 3 in the ISO model, and UDP is layer 4 of the transport layer. Observation. You've heard of TCP IP, Transmission Control Protocol. TCP guarantees data delivery. It does this when it says, I send you a message, you must acknowledge every byte of that message that I sent with TCP. In this fast world of sending out messages, there is not time to acknowledge every message. And that is UDP. UDP does not acknowledge a message. It sends it out and says, here it is. If you get it, good. If you don't get it, not my problem. You have to look at other ways of recouping that lost data. So both goose and the sample value message do not look for lost data. They have other mechanisms to recover. The way they recover is they send the message over and over and over again. So what the goose does, it says at time 0, the breaker's open. 4 milliseconds later, it can repeat the message and say, the breaker's open. 8 milliseconds later, it can repeat the message and say, the breaker's open. So by repetition, unless your network is down, that message will eventually get through. That's how goose and sample values, actually sample values not as much, but definitely goose works. You see on this picture a brand new profile. In fact, this profile is literally in process of being ratified as I speak here. It is in the final stage of ratification in the IEC that will become a new part of the IEC 61850 standard. And this is the Precision Time Protocol, or PTP. PTP is a way of communicating precision time over Ethernet. What is precision time? Plus and minus 100 nanoseconds of absolute time, typically. So in a substation, we're the only place we need, actually take it back, we need this today in 2 different applications. The first application is for sample values. This would have been the process bus material that Steve talked about. The second application is when we compute synchrophasors. Both of those applications need precision time. So there is now a profile that's part of 61850 that defines how to implement precision time. Later on, assuming I have enough time here, I will talk about how this precision time protocol works. So, what does the new routable goose bring to the party? So, the first observation is this goose is going to go out into the wild. So if you're going to send a goose out into the wild, it better be protected. So the first major addition when the R goose and R sample values were created, they were created with a complete security implementation. So these messages are designed to go out in the wild and to transverse with impunity. And how do we do security? We're going to talk about that in a minute. In general, however, security needs a key to lock the message. What you see in this picture here are several of the data fields that are part of the Argus message that communicate the key timing information. If you ever notice on apartments, many apartments, when a tenant moves out, what do they do on the apartment? They change the lock so that if the tenant has the old key, they can't get back into the apartment. That exact same concept is brought forward today with the routable goose. Every 48 hours, every 2 days right now, the system is designed to change all the keys on all the locks on all the messages. So that if someone gets kicked out of the group or someone figures out how to crack the key, well, let's put it this way, it gives a person trying to crack the key only 2 days to do it. And to date, no one has ever done that. So again, changing it every 2 days is a very, very good way of enhancing security of the message. The message, in this part here, this is what's called the session protocol data unit. The session has information for the keys. It has a payload. The payload is the message we're sending. This is going to be the goose message. What's an application? Let's say I have a distributed energy resource. I have a solar inverter on a house. In fact, more than that, I have 100 solar inverters on a feeder in the utility. And I want to regulate the voltage on that feeder. Today's solar inverters are at least 2-quadrant and sometimes 4-quadrant inverters. What does that mean? If it's a 2-quadrant inverters, that means I could adjust the VARs plus and minus. So the inverter can put out the volt amperes via VARs either in a plus range or a minus range. That requires control. How do you get the control to these devices and quickly? I'm positing that the secured routable goose is the mechanism to do this. By running this secure goose over a secure radio network, for example, today's radios, running at 900 megahertz, have a latency of only 5 milliseconds. So that means within 5 milliseconds, I can get a voltage control message to literally hundreds of thousands or even millions of solar inverters all around the state of California, and doing it securely. The last item on this is something called a signature. And we're going to talk about this in a little more detail, but this authenticates the message. In Roman times, the Roman emperor had a seal. When he wrote a message, he would stamp his seal on that message. That would authenticate that message that it came from the Roman emperor. The signature is the exact same thing. It's a seal that gets put on the message that authenticates and says, this message must have come from Mark. Nobody else could have created this signature on this message. So simply stated, what was done is that this top piece of this slide shows what's called the Protocol Data Unit, or PDU. This is the goose message. These are the data items that are incorporated as part of a communication message. For example, going down to a solar inverter, these would be set points for voltage. These would be set points for output power. In a 4-quadrant inverter, by the way, a 4-quadrant means not only can I regulate VARs, I can regulate power flow, either plus or minus power flow. This will happen as solar inverters are integrated with battery storage systems in the home or wherever they're located. So that means I can either take energy from the battery or put energy into the battery from the solar inverter. Adding on to this protocol data unit, what you see there is UDP, User Datagram Protocol, and you see an IP layer there, either IP version 4, or I think you realize we are in transition to IP version 6. I will say though, however, if you're just inside the utility, a utility can operate quite gracefully with IP version 4 for a very, very long time to come, because there is a non-routable version of IP address that most utilities use today that keep them secure from the outside world. And so I expect to see that taking hold for a long, long time to come, and the utilities will not be forced, at least internally, to migrate to IP version 6, except the one major driver here are meters. When you take millions of meters out in the open there and you want to be able to access each meter individually, then the industry is migrating to IP version 6. IP version 6 has I don't even know how to pronounce the number. Well, it's 2 to the 128th addresses. And that's a very, very, very big number. Just want to illustrate again the concept of unicast versus multicast. So today, if I have a piece of data in a substation, which is this left dot here, where's my mouse? It's operating strange today. Anyway, the left picture shows the concept of unicast. So let's say I had a phaser measurement unit, that red dot on the left, and it wanted to send synchro phaser data to 3 different control centers. In the unicast mode, it would literally have 3 connections from that one red dot to the 3 remote stations. This requires 3 times the bandwidth on the link from the phaser measurement unit to that first red dot. When we go to multicast, which is the figure on the right, the red dot sends one message to the next router. That router is now smart to say, oh, I need to send a copy to the green dot on the left, to the green dot on the right, and to forward a copy to the next router. This is how multicast works in our world. So I just want to review what's interesting in our industry. Even though we may be power engineers, we're being forced to become communication engineers also, because we need to understand how the communications are going to work on the power system. And multicast requires a new communication protocol for us. It's called IGMP, Internet Gateway Management Protocol. What does IGMP do? This relates back to my example of how do you tune in an internet radio station. What you do is you go searching for the station. You say, please go and find WQXR, which is the name of the radio station. So your computer sends out a message looking for the name of that radio station. This is exactly what happens now with a relay. The subscriber, the device on the right, says, I want to go listen to Mark. I want to see what Mark has to say. So the device, the subscriber on the right, sends out this new type of message, this Internet Gateway Management Protocol message, and says, go find Mark. And it literally uses new type of routing algorithm called Protocol Independent Multicast, PIM. So remember that, because as you purchase new routers for your system, you want to make sure that the routers support Protocol Independent Multicast. The routers will search and look for Mark. When they find Mark, they lay down a bunch of breadcrumbs so that now, when Mark publishes his message, the message follows the breadcrumbs and gets to the subscriber at the end. Now, when you're listening to an internet radio station, you ever notice periodically you'll get a message on your screen, and the message says, "Are you still there?" Why is it doing that? Well, just think, if every one of us created a link to the station and never broke it down, you'd have thousands of inactive links all across the internet. So one of the other features of the Internet Gateway Management Protocol is a automatic breakdown feature. So if the subscriber on the right goes, well, what happens is that what's called the local multicast router, that local multicast router periodically sends a message to the subscriber and says, "Are you still there?" If the subscriber does not answer, that entire multicast path is broken down. And so you're not just broadcasting into thin air with that message anymore. So that is how multicast works. I will mention there are a block of multicast addresses that are part of the IP version 4 messaging hierarchy, if you will. And you must use those multicast addresses in order to establish multicast paths. I'm sure you've heard today about the substation configuration language. Since this is still part of 61850, the data sets for Goose and the data sets for the sample values can be created using those standard 61850 substation configuration language tools. So that's, again, this is just a natural extension of 61850 for configuring data sets and transmitting data sets over the network. This is just an example of what the data set creation looks like. So, security. How do we secure a message going out into the wild? There are 3 aspects. Actually, we're going to say 4 aspects of data security. This slide only addresses 3. I forgot to add the 4th in here. The first aspect, actually, that's the first one I'm going to talk about, is how do I know that if I want to send a message to Alex, how do I know that he is Alex? The way we do this now, he can't deny it. That's the beauty of this thing here. He can't deny he's Alex, because he has a signature. You know, he has a certain tonality and a certain style of talking, so that when I communicate with him, I can uniquely identify that that is Alex. In the world going forward, we do this using something called a certificate. A certificate is a document that where all the elements of the document are scanned. If you ever, do you know something what's called a CRC? A cyclic redundancy code, CRC. A CRC is a hash where all the bytes in a message are scrambled together in a very specific pattern. This is how a certificate works. All the bytes of the certificate are scrambled together, and then at the end, that combination of all those bytes is locked with a key. That locked message is called a secure hash. And And the only way that you could validate and create that secure hash is if you know the key. So this is the first. So Alex has a certificate. I can say to Alex, Alex, show me your certificate. And when he does, I can validate that he is Alex. And I can say, okay, Alex, you are a approved recipient of my data. So I will send you a key so that you can authenticate and you can decrypt the message. So the first part is a certificate. The second part I just talked about is the hash code. So when a message goes out, all the bytes in the message are scrambled together and then locked with a key. This is called a signature. If you can unlock and revalidate that message, you have authenticated that message, saying this message could not have come from anybody else but Mark. So when Alex gets it, he can unlock it and authenticate, yes, this came from Mark. The other aspect of security is encryption. You may not want to be exposing the information that you're sending out over the wire. And the mechanism for doing this is called encryption. It turns out for our industry, the 61850 has adopted a standardized encryption algorithm. The standard algorithm is called AES, the Advanced Encryption Standard. So what we have here, by choosing a standardized encryption, we have interoperable security. So that means if I have a GE and an ABB and a Schweitzer device, and they adhere to the standards, then we can interoperate with security. And that's the goal for 61850, interoperable security. The last piece I'll talk about real quick on the security element is how do I exchange the keys with all of the members? And this has two elements to it. The first is developing the concept of a security group. A security group is a publisher and all of the people who are subscribing to the publisher. So this is known as a security group. So the first thing that has to happen, is that there's an element who is going to distribute the keys. This element is known as a key distribution center, or a KDC. The KDC has settings, and the settings are, okay, the security group is going to be Mark, Wendy, and Alex. So the three of us are going to communicate together. And the key distribution center knows this, and the key distribution center will validate our certificates, that we have valid certificates and are part of this defined security group. Once the KDC validates the group, it then says, okay, Mark, Wendy, and Alex, here is your new symmetric key. Now notice the word I used there, symmetric. That means when I lock the message, I lock it with a key. The exact same key has been sent to Wendy and to Alex, and so when they want to unlock it, they use the same key. So that's the concept of a symmetric key algorithm. The exchange of the keys, however, is done using an asymmetric key. This is what's called a public-private key pair. The exchange is done by an internet standard known as the Group Domain of Interpretation, GDOI, which is an internet standard, IETF 6407. And this standard defines how to exchange keys between all the members of a group. This is all spelled out very, very clearly in the 61850 standard. And this will be part, by the way, 61850 is going through 2 revisions. It's going through I'll call it a half revision right now. There's going to be an edition 2.1 that will be released, I'll say the next year. And this will and the 2.1 half release will incorporate these features of security and the routable goose and routable sample values. We've talked about the compression already, I'll skip that. Again, the hash function just takes all the data in the message, mixes it together in a very specific algorithm, comes out with a what is known as a hash code, and that hash code is locked with a key. So when one device sends the hash code, it creates what is known as a message authentication code, or oftentimes known as a hashed message authentication code. And that is the signature you saw attached to the bottom of that protocol data unit. The receiver receives the message. It rehashes the message. It has the key. It relocks, it creates that same secure hash. If the transmitted hash equals the received hash, that message is authenticated. Nobody could have gone in and changed the message to get that exact same number. How big are these hashes? Now, who knows how big is a CRC? Anyone know? Ethernet CRC, anyone have any idea? You know, how much? 32 bits in an Ethernet cyclical redundancy code. The secure hash is 256 bits. Very, very secure. And cryptography. All right. The next piece I was going to, there's a couple of things. Just real quickly, what the other part of this, so this group domain of interpretation, in fact, right now, we have created a utility-specific version of this GDOI. So what's specific about it for the utility world? In the utility world, dependability is key. I have to be, if there's a fault on the system, I have to be able to trip to clear that fault. If a remedial action scheme requires a control message, I have to be able to transmit and receive that remedial action message. That trumps security. The dependability is more important than security in the utility world. And what I'm talking about is, what if I sent Alex the key and he wasn't home when I sent it? He didn't get a new key. So when he comes home, guess what? He's locked out of his house. He can no longer receive any messages from me, which is not good. We really want Alex to get home sometime. He's not home often. When he does get there, we want to make sure he gets into his house. So a variant of this group domain of interpretation was created for the utility industry. And right now there are 2 pending IETFs we need to get through, the Internet Engineering Task Force. And this is the concept of key delivery assurance. What this says is, I'm not going to send out the message using the new key until I have a guarantee that Alex got the new key. Only then will I change the locks on all the doors in the house. So this is a utility-specific implementation of the group domain of interpretation. And this picture just kind of shows this. I won't go into more detail than that. I've explained it better than the picture shows it. All right, the other aspect of change in 61850 is the adoption of the precision time protocol. What is the precision time protocol? In fact, I'm going to harken back. I love the old World War II movies. And in the World War II movies, you see the commander says, okay team, everybody synchronize your watches. On my mark, the time is 1:55. Mark. What's the error between my watch and your watches? Well, there are going to be several aspects. The first is communication. My voice travels through the air at the speed of sound, and which means it takes time. Like by the time it gets to Stephen back there, it's already like 2 milliseconds delay. Okay? So there is a known travel time through the air that delays the time. Steve has to receive the message, so there's a delay time in going through his hearing process. He has to think about it, so there's a processing delay. And then he's got to push the button on his watch, which is an actuation delay. In theory, all of those delays are measurable. That theory is put into practice with the precision time protocol, where all the delays in sending a message from a GPS master clock in a substation to all the relays, or IEDs, I'll use the term, in the substation are measurable. And this is exactly what PTP does. It defines a system for measuring all the delays in communication of time. And of course, all starts with GPS, the Global Positioning System. So here's a trivia question. To whom do we owe the most for GPS?
Military.
It's a trick question. The answer is the Russians. In 1957, what happened? The Russians launched Sputnik. What was Sputnik? Sputnik was a bomb where they took the fissile material out and they put in a radio. So flying around the Earth is Sputnik and sending out a radio signal. Have you ever stood on a street corner and had an ambulance drive by? As the ambulance approaches you, it has a one frequency, and as from the siren, and as it leaves you, you hear a different frequency. This is known as Doppler shift. That satellite, as it's flying by, is transmitting a radio signal. As it's coming at a tracking station, it has one frequency, and as it passes the tracking station, it is received at a different frequency. So by tracking the Doppler shift on the satellite, they could tell exactly where the satellite was in the sky. Now, this is where the Americans came in, and they said, well, gee, this is interesting. If we can tell where the satellite is by looking at the Doppler shift, what if we knew where the satellites were? We could figure out where we are. And so this was the origins of GPS, is by applying what was learned from tracking of Sputnik to developing a satellite system here on Earth. But we have more to thank for the Russians. When GPS was first built, it was a closed system. It was military only. In 1983, Korean Air Flight 007 strayed into Russian airspace. The Russians shot it down, and the problem was clear. Didn't know where it was. The President of the United States then was Ronald Reagan, and Ronald Reagan says, can't have this happening anymore. He made the decision to open up GPS to the world. So we thank the Russians again for enabling that to happen. So that is the origin of GPS. Going forward, a constellation of satellites now exists around in a low, we'll call it relatively low orbit. These satellites fly, let's see, do I have it here? There it is, 20,000 kilometers is the altitude of these satellites. And you see there are 6 orbital planes, 4 satellites in each orbital plane. So there are a total of 24 satellites Y24, at any location on the Earth, at any instant in time, 4 satellites are always visible. And with 4 satellites, you can compute location and time with extreme precision. So that's the concept behind the GPS satellites out there. So this is now our source of time as we go forward in almost everything we do in our world. So how does a GPS clock system work? So the GPS sends down a 1 pulse per second signal. It comes down at about 1.5 gigahertz, and it comes into an antenna. All the antennas on the GPS system are base loaded, which means there's an amplifier in every antenna, because the signal is so small, it comes in at about a minus 150 dB. Very, very low signal, so there's an instant amplification at the antenna. So the antenna picks up the signal, amplifies it, and sends it down to a receiver. Observation, if you have a 100-foot antenna, you're going to get 100, what the time delay of sending that electrical signal through the antenna cable is 1 nanosecond per foot. So the GPS receiver has to know this, and this is a setting inside your GPS clock. So you need to compensate for the length of your antenna lead inside the GPS clock. Inside the clock there's a receiver that receives the signal from many devices of satellites simultaneously, and then the receiver disciplines an oscillator. So an oscillator, you buy an oscillator and say it's going to oscillate at 1 megahertz. There is always a precision on that oscillator that says, well, it's plus or minus 1%, plus or minus 0.5%. Given that error, if it was left undisciplined, it would drift. So what the satellite does is send down a disciplined time signal, and that is used to adjust dynamically the frequency of the oscillator inside the GPS clock. Actually, I do want to mention one other thing. These satellites are flying around the Earth, and they're moving faster than we are. What does Einstein tell us about that? Their clocks run slow. So relativity actually plays a part in the GPS system. So as all the GPS clocks are cesium clocks inside the satellites there, but since they're moving faster than we are, their clocks slow down. We're talking about nanoseconds, but the people who do these things are kind of anal about that, and so they actually go in, it has to be corrected. Every so often they have to go in and correct the clocks to adjust for relativity in those satellites. Now, on the oscillator side, in our industry today, there are 2 or 3 different types of crystals. Actually, I would say mostly 2 different types of crystals that are used in our industry. There's oscillators. There's crystal, and then there are rubidium oscillators. The difference in these is what is known as the stability. Why do we care about stability? I've heard in this area of California you have these crazy things called earthquakes. What do earthquakes tend to do? Break down structures. What's the main structure we're concerned about? And by the way, the #1 failure mode in a GPS system is the antenna. So you get the antenna knocked down, I'm no longer disciplining my oscillator. What's it going to do? It's going to drift on me. How much it drifts is known as the stability of the oscillator. A crystal oscillator has a stability of about 1 part in 10 to the minus 9th. So that for 10 to the 9th, for 10 to the 9th oscillations, it has a potential error of 1 part in 10 to the 9th. The more robust oscillator is the rubidium oscillator. It has a stability in 1 part in 10 to the 12th. Very, very stable, but there's no, as we say, there is no free lunch. You can buy the rubidium oscillator. They cost more money, but they wear out faster also. There's actually a wear factor in oscillators. And so the oscillators, even though it's more stable, will fail quicker than a crystal oscillator will fail. So these are choices you get to make in your industry. Coming out of this clock, I will have 2 primary communication types. The first one we've used for eons, which I call a de facto standard, is IRIG level B. And IRIG level B can be very, when the message comes out, the on-time pulse of an IRIG B message will be plus or minus about 100 nanoseconds. So it's as good as 1588. 1588 can get a little bit better because it has a little more control over the time delays in the communication path. Boy, you can't read that, can you? It's a good thing you have notes in your books there. And then that exact same clock can also now put out, thank you. That exact same clock could also put out a IEEE 1588. IEEE 1588 is the standard number that defines the precision time protocol. So, now, these are the 2 primary functions of a GPS clock, but you will also find most GPS clocks also put out something called a 1 pulse per second time signal. But 1 pulse per second doesn't identify the pulse, so that has to be incorporated with a communication message that identifies the name of that pulse. The name obviously is the time when that pulse was emitted. Many clocks today will also put out something called the Network Time Protocol, or NTP, or sometimes you see it called SNTP for Simple Network Time Protocol. The Network Time Protocol and 1588 both use the mechanism of the master sending out a time and then the system estimating or calculating as best as possible the delay from me to from the clock publisher to the receivers in the system. IEC 61850 does define what are called time synchronization classes. And what we see in this chart here, we see for SIMP there's a T4 and a T5 class. Either T4 or T5 class, which T4 is a 4 microsecond accuracy and T5 is a 1 microsecond accuracy. It's an argument one can make. Either class is quite acceptable for sample values and for synchrophasers. So the scope of IEEE 1588 is to provide a network communications to synchronize clocks around a system. The goal is sub-microsecond, and that's easily implementable today, all with off-the-shelf Ethernet chips. You can easily do sub-microsecond time synchronization. An interesting aspect this is a Mark personal item I'm trying to move forward. I'll probably try to recruit Alex along the way, but it's messaging. What else does a GPS clock know? It knows where it is. It knows latitude, longitude, altitude. As a relay, I could send out a message to the clock and say, where am I? And the clock could literally reply with the latitude, longitude, and altitude. So Alex and Steve, this is one of my new my new tasks going forward. New function I'm going to add on to 9-3. In general, so PTP has a network of clocks. The main clock in a facility is known as the Grand Master. The Grand Master synchronizes a slave below it. That slave synchronizes a slave below it, etc. In our world, there are going to be primarily 3 types of clocks we will see. The first kind of clock is called an ordinary clock, and that's the Grand Master is an ordinary clock, and the relay is an ordinary clock. An ordinary clock has one terminal, one input to synchronize itself. The Grand Master has one output to send the sync message. So an ordinary clock has one connection point. The second kind of clock we're going to see is something called a transparent clock. In an Ethernet network, how do we build the network? We use devices called Ethernet switches. When I send a message to an Ethernet switch, there's a time delay in going through that Ethernet switch. So going forward, when you implement these systems, you will have to use, you should be using, you don't have to, but if you want to get precision time, you should be using Ethernet switches that can measure what is known as the residence time of the message going through the Ethernet switch. So Ethernet switches are called transparent clocks. The third type of clock that's of interest to this group here is something called a boundary clock. And a boundary clock sits on the boundary between, say, the Grand Master and some other synchronization function in a system. Where do we see this applied? Process bus. So one of the architectures of process bus is, and then there are multiple architectures that can be implemented as part of the 61850 process bus standard. One of them is where the Grand Master synchronizes the relay, and then the relay synchronizes the merging units within a zone of protection. So that means if the Grand Master fails, the relay takes over as the synchronizing source for the merging units in a protection system. So this allows the user to isolate zones of protection inside of a substation. And there are 2 architectures that can be implemented using the existing standard. So these are the types of clocks. Next slide, we just talked about them. So how does this basic concept work? So we're going to start with what is known as today as a 1-step clock. I will explain the difference between 1-step and 2-step. But in general, on the left, you see the Grand Master clock. The Grand Master clock sends out a synchronizing message, termed a sync message. This is my analogy back to the Army commander that says, okay, the time is now 2:14, okay? So that message is a message coming out from the Grand Master. It's an Ethernet message, and that message contains the time. By the way, a very important point, PTP uses a different time base than we're on right now. We're on what's called UTC, Universal Time Coordinated. PTP sends data out on what is called TAI, Time Atomic International. Today, there is a 36-second difference between TAI and UTC. So it's a simple calculation, but it has to be done. The message that gets sent out from the Grand Master contains what the offset is at an instant in time. So that is part of the message communicated from the Grand Master clock. So at time T1, the message comes out. It arrives at time T2 inside the relay. So the relay has its own time base. Sometime later, the relay thinks about it, and at time T3, it sends a message back to the Grand Master. And the message is, tell me when this message arrives back at the Grand Master. The Grand Master turns it around and says, okay, here is the time when I received your response. So the relay now has 4 timestamps: T1, T2, T3, and T4. How do I calculate my precise time? Well, it's a very, very simple calculation. So the first part of the calculation is I want to eliminate the time inside the relay. So the time inside the relay is T3 minus T2. When I do that, watch what's going to happen here. When I subtract out T3 minus T2, what do I have now? Round trip time. What is the round trip time equal to? Well, you can see pretty clearly it's T4, time 4, minus T1 divided by 2. Key assumption here. This assumes that the forward time delay is equal to the return time delay. And this is a major assumption inside PTP, that the forward time delay is equal to the reverse time delay. All of these timestamps are made inside of the Ethernet chip inside the relay today. Or with any device, any IED that uses PTP has to have a special Ethernet chip that makes these calculations. And makes these timestamps. All the timestamps are timestamped to the nearest 1 nanosecond. That's the resolution of the timestamps. Not the accuracy necessarily, but the resolution. For completeness, you might hear something called a 2-step clock. There are very, very few of them left out there, but when 1588 at first, the first 1588 clocks took 2 steps to communicate the T1 timestamp. Remember, T1 is the time when the message came out. Today's Ethernet chips are fast enough so that on the fly, as the message is leaving the Ethernet chip can put that timestamp into the message. In the original silicon, where this was done, the Ethernet chips were not fast enough. And so what happened, there was a follow-up message that was sent that said, by the way, here is the timestamp when this message was sent out. And that is called a 2-step clock, because it takes 2 steps to communicate the time, the T1 time. But I've been involved in this for 5 years now, and I have never seen a 2-step clock yet. So I doubt you will either. The timestamp, as I mentioned, is in TAI. It has 48 bits for seconds, and it has 32 bits that count nanoseconds. So there are obviously 1 billion nanoseconds in a second. So this bottom field counts is modulo 1 billion. And the top one counts seconds starting January 1st, 1970. January 1st, 1970 is the epoch of the precision time protocol. It also happens to be the birthday of Unix, because Unix also has the same epoch or starting time, except the Unix time and TAI differ by about 9 seconds. And I think that the French got it wrong, but that's such is life. By the way, TAI is, my French is lousy, but it's like Time Atomique Internationale in French. And so it was really, it was a French standard that created TAI. Where I want to go to here is, where is this timestamp measured? I didn't go into Ethernet in detail here, but suffice to say, in an Ethernet data frame, Ethernet is self-synchronizing. It means it has a sync pulse that's built into the message. When an Ethernet frame first comes out, it sends out a square wave, a 1010 pulse. This square wave synchronizes an internal phase lock loop in the Ethernet chip. But of note, there is one point where it goes 101011. At the end of that 1 pulse, that is where the timestamp is applied to the outgoing Ethernet message. And again, that timestamp is measured to the nearest 1 nanosecond of resolution going out of the Ethernet chip. That's where the timestamp is applied. So in a substation, we have an architecture that looks like a grandmaster, an Ethernet switch, and then many, many substation devices connected to the Ethernet switch. The goal here is that all the substation devices are synchronized to the same grandmaster clock. There are, yes, I forgot, questions are allowed here.
I just want to clarify, these Ethernet paths are deterministic because you're using a multicast protocol?
These are not deterministic.
Oh,
They calculate the delays on the fly. Every message calculates its own delay. So hold that thought, because I'm going to show you where we remove the variability.
okay.
And it does happen. It's a good question, though. Actually, well, this one, tell you what, I'm going to jump ahead since you asked the question. This next slide shows this. This,
Nobody can read it.
yes, that's in your books.
Maybe in the books.
You didn't get a book. You can share, Alex.
Probably you can't read it either.
Okay, unfortunately, yes, it's hard to, I got to change the color scheme on that one here. So, to answer the question, you're right, there is variance, and the primary source of variance is the Ethernet switch. The timestamp on the outgoing message is fixed, because it's put in hardware. The timestamp on the incoming message is fixed. It's also done in hardware. The variance is in the middle in the Ethernet switch. When the message comes in, there is something that the term they use is residence time inside the Ethernet switch. There are special Ethernet switches that are 1588 aware. So that means you do need to use a 1588 Ethernet switch. If you want to get precision time, you need to be using a 1588 aware Ethernet switch. What it does, in this picture you can't see, is it measures, it timestamps when the message enters the Ethernet switch, and it timestamps when the message leaves the Ethernet switch. The difference between ingress and egress time is known as the residence time. The residence time is added to the correction field in the Ethernet message. So that time is accounted for dynamically. So every message that comes into the Ethernet switch has a different residence time that is calculated. So it's completely variable depending upon how busy the Ethernet switch is on any given message.
And if there are two switches that add in.
Exactly. Each switch is responsible for adding in its residence time. Let's go back here now. There are two mechanisms that are defined in the 1588 standard for measuring the total delay time. The first mechanism is called end-to-end delay calculation. On an end-to-end basis, the communication is between the grandmaster and the device. So the grandmaster sends out the sync pulse, the device receives it, and then sends back the delay request to the grandmaster. The grandmaster sends back the T4 timestamp. The relay now has 4 timestamps. It computes the total delay. Notice what you see here. When it goes through the Ethernet switch, also called the transparent clock, you see that the transparent clock measures the residence time inside the transparent clock. And notice, it gets measured in each direction. So there's a forward delay measurement and a reverse delay measurement. Now, an interesting observation here that does assume that the forward and the reverse time delays are somewhat equal. What we've seen, the variance is not that great. And so the variance is not going to affect, say, hitting 100 nanosecond time accuracy right now. This method, however, yes?
What will be the variance in the residence time delay, depending on how busy the switch is?
Yes.
What's the actual variance?
I don't know the answer to that one. What we do know, when we tested this, in fact, we tested at PG&E, we compared IRIG-B to 1588. And what we saw, that in general, the variance between the two was plus or minus 100 nanoseconds between IRIG-B and 1588. And we didn't really see the variance getting anything beyond that. Now, this end-to-end test has been eschewed by the utility industry. They said, but this is the working groups that are putting together the standards for 61850. They said, we don't want to do the end-to-end. We want to do what's called peer delay. And the peer delay eliminates that variance in the Ethernet switch residence time. And here's how peer-to-peer delay works. Now, the grandmaster sends out the sync message at time T1. And the message goes to the Ethernet switch. What is very fixed, however, is the time delay from the Ethernet switch to the grandmaster. So that round-trip time between the Ethernet switch and the grandmaster is very, very regular. There's no variance in that time delay. So the peer delay mechanism requires that each device in the path calculate the wire time delay. So in this case here, from the Ethernet switch to the grandmaster, and then from the relay to the Ethernet switch. Those are going to be very, very constant numbers, because it's only the time on the wire. So in the peer delay mechanism, when the message comes to the transparent clock, the Ethernet switch, it knows what the delay is from it to the grandmaster. It puts that message in to the correction field of the message, and it also puts in the residence time of the switch in that one-way direction. So I'm no longer concerned about variance between forward and reverse time delay. Using the period delay mechanism, it eliminates that error in the time synchronization. So this is what the utility industry has chosen. It says if you use the 9-3 profile of 61850, this is how you calculate the delays through the network. I will not go through this, but you keep hearing me reference the correction field. Every 1588 message has this exact same format, and the one field that you cannot read again, but it's in your, it's a good thing that they have handouts. So in your handouts, it points out exactly where that correction field is. That's the number that is dynamically updated as the sync message transits through an Ethernet network. Some details. As I mentioned, the epoch of the beginning of counting seconds for TAI is January 1st, 1970. TAI and GPS run in parallel. There is a 19-second difference between GPS time and TAI time. And then between TAI and UTC, actually this presentation goes back before June 30th of 2015, but the last leap second we had was June 30th, 2015, and the difference between TAI and UTC increased to 36 seconds. And that's where we are today, right now. So to go from TAI to UTC, you just subtract 36 seconds there, or add 36 seconds to the TAI time. A very interesting option for 1588 is the ability to work with multiple grand masters. In the utility industry, we are highly focused on availability. Today, in a substation, there will only typically be one GPS clock. And I can at least speak for the GE relays. On the GE relays, we only have one IRIG-B port. If that one clock feeding that one port fails, you've lost time synchronization, or at least you've lost accurate time synchronization in that device, and it will start to drift because it's now running on its own internal clock. 1588, I'm on an Ethernet network. I can now have multiple grandmaster clocks in my substation. And even today, an IED can dynamically switch from grandmaster number 1 to grandmaster number 2 to grandmaster number 3, or as many grandmasters as you wish in a substation. So we now have a much higher availability of time sync in a substation. How does a relay choose a grandmaster? I think of it almost like birds choosing a mate. You know, you compare different aspects of the mate. Same thing happens in GPS clocks. A GPS clock advertises its capability. It says, I am GPS number 1, I have an accuracy of 100 nanoseconds, and it lists a whole range of different characteristics of that grandmaster clock. Grandmaster number 2 says, I'm grandmaster number 2, and here are all my characteristics. So as a receiver, I receive both announce messages. I get to choose the grandmaster I like best, or it is typically called the best grandmaster, best master algorithm, or BMC, best master, whatever. But I choose based upon this list of characteristics. There is always a tiebreaker, because when the clocks are configured in the substation, one clock is always configured as grandmaster number 1, The other one is configured as grandmaster number 2, grandmaster number 3. So if everything else is the same, the relay will always choose the one that's labeled grandmaster number 1. Something that we will be using, and this will be mostly hidden from you, but there is a failure mode. As I mentioned that the number 1 failure mode in the GPS clock is the antenna. If I lose the antenna, my GPS clock is still pretty good. I mean, with a crystal oscillator, I'm going to only drift 1 microsecond in 4 hours. If you have the rubidium clock, like some people do, the rubidiums will only drift 1 microsecond in 4 or 5 days. That's how stable the rubidium oscillators are. But how do I know when I've lost synchronization to the satellite and or my antenna has failed? There is a message that's part of the precision time protocol, and something called a clock class attribute. And it's a number. And as far as you're concerned, this is going to show up as a sequence of events message that says, hey, you've lost synchronism with the satellite. That's what you're going to see. Just so you know, internally there's a number that comes back from the clock, and the clock is either a clock class 6, which is I'm synchronized to a GPS satellite, or it's clock class 7 that says I was synchronized, I've lost connection to a satellite. So this is some details that you don't need to know, but it's there. All right, a couple of, finish up here now. About 3 o'clock? Yes?
Yeah, so the TTP is for Ethernet, but you mentioned in the beginning, like you wanted maybe to stretch outside of the substation and you had the firewall there and everything. Has anyone thought about, taking it?
Very good question. All I've been talking about right now, so that's a very good question. Let me expand a little bit on that. So 1588 is time synchronization for the entire world, for all aspects of communications. In the utility world, we tended to focus only inside the substation. So as a result, we have created a profile that only works on a local area network. It means there's no IP address in the message. So the profile I've been talking about is only inside the substation. To your point, there is another profile. There's a profile called the telecom profile. The telecom profile is designed to work wide area, where it can go through multiple routers. And so you can synchronize out into a much wider area using the telecom profile. So that's what has to be done in these cases. But the 9-3 that is part of 61850 is only defined inside the substation on a local area network. No IP address. Good question. Thank you. All right, so we've talked about some of these, well, we talked about messaging, and we started off with Goose messaging. So where is Goose being used today? So, first question, can anybody identify where this beautiful water scene is taking place? Phoenix, Arizona? Yeah, this is Palo Verde. This is Palo Verde nuclear power plant. There are 3 units at Palo Verde. Oh, probably 10 years ago, they upgraded the rotors on these generators. When they upgraded the rotors, they increased the output power by 150 megawatts from these units. Now, as you know, the Western Area Coordinating Committee, WEC, is responsible for reliable operation of the electric power grid. Well, one of the studies they did is, what if 2 of the 3 Palo Verde units go out? Just, fail and go offline. They did the study, and lo and behold, the line, the California-Oregon intertie, it's COI. Anyone know the path number for COI? 66, 65. Turns out that path overloads. So if 2 of the Palo Verde units go out, COI overloads. So WEC said to SRP, guys, you gotta fix it. So the fix was Salt River decided to shed 150 megawatts of load in the Phoenix, Arizona area. This had to be shed in less than 1 second. So how do you communicate from Palo Verde to all of downtown Phoenix to shed load? The answer? Goose. Goose to the rescue. So this is the picture. Let's see. It doesn't identify the path on this one here, but it's the Malin Round Mountain 1 and 2 and Captain Jack Olinda lines that overload on loss of 2 of the Palo Verde units. Again, the only takeaway here has to happen in less than 1 second. So a system was put in, and this has been in service now for, I'd say, almost 10 years at Palo Verde, and they measure the output power from all 3 Palo Verde units, and if 2 of the 3 outputs sum to 2550 megawatts, it arms the system. Arming the system says, identify loads in downtown Phoenix that can be shed on loss of the 2 Palo Verde units. An interesting challenge that had to be addressed was, well, they chose 14 substations. And the average load of the 14 substations was about 250 megawatts. But guess what happens in the summertime in Phoenix, Arizona? It gets very warm down there. Everyone turns on the air conditioners, and so as a result, those same 14 substations now sum up to about 600 megawatts. So tripping the same 14 substations would significantly overkill the amount of load that had to be shed. So the scheme was put into place that dynamically calculated the power in each of the substations. And so it would add 1 substation at a time to the list to be shed. And when it hit by the way, they chose 250 to put it for a safe margin. When they hit 250, they stopped and they had their system armed and ready to trip in Palo Verde. How were the trip messages sent? Goose. Now, this was old Goose. This was back in about 2005, 2006 timeframe. Our Goose did not exist. But luckily, Salt River was able to develop a local area network over all of Phoenix, Arizona. They had a SONET communication network, and the SONET created literally a local area network of all substations in the Phoenix, Arizona area. So 1 Goose message sent out would literally go to every substation in Phoenix, Arizona. How quick was that? We'll skip this part here. This is the SRP SONET network. This picture here shows on the far left is Palo Verde, and then you see Phoenix, Arizona. All the little black dots on that map you have are the substations that were identified for load shed in the Phoenix area. In doing testing of the system, the round trip time from Palo Verde to a substation and back again, round trip measured time is 14 milliseconds. That means one way messaging time to hit all those substations is 7 milliseconds using Goose messaging. Another application, your neighbor to the south, Southern California Edison, has developed something called the Centralized Remedial Action Scheme, or CRAS. The idea being that there's a wide range of situations that call for remedial action in the Southern Cal system. CRAS, or centralized RAS, says I have one main controller. The one main controller collects operating conditions from around the entire Southern Cal system. It makes a dynamic decision. It says, is there a remedial situation that needs to be mitigated? If a situation, now what are they? The planning people at Southern Cal identified, okay, if this and this happens and this line overloads, I have to shed load here. So there was a series of identified remedial actions from the planning department that are incorporated in this. If those situations are identified, an identified remedial action also exists. Guess how they do this? Goose. I want to hear it, come on. If you're learning one word from this seminar, it's going to be goose. Actually, I'll point out that when 61850 came out, the first part of it that was truly implemented were the goose applications, because there was immediate benefit that could be seen from using the goose communications. Client server came along a little slower in the application realm. So again, in a remedial action scheme, you have three elements. You have a monitoring section, you have a calculation section, and you have a mitigation section. All of these are communicating back and forth using Goose messaging. Another aspect of this, the configuration of the entire system is done using the substation configuration language. So when a mitigation device publishes measurements, there are definitions of those measurements in what is called the configured IED description file. Did you guys talk about CIDs and ICDs and things like that? Very little bit? Okay. So there's a new name for the setting files inside of a relay. That new name, if you implement it to 61850, it is called a configured IED description file, or a CID file. The CID file contains what are called data sets. A data set has a list of data elements that are being monitored in a given substation. So when you configure the centralized host computer, the input configuration file is the settings file from the relay. And that central controller can read that file and immediately identify those elements that are coming in, that are available to feed into remedial action schemes. Same thing happens on the output side. An output Goose message is sent to do the mitigation or the tripping of loads or whatever the mitigation function is. Those are also defined in the CID file of the relay. Bottom line performance, these are actual measurements of a LUGO line out remedial action scheme. Round trip times, you see that the tall blue ones there are the round trip communication times on the order of 11 to 12 milliseconds. Round trip over 600 miles right now in these remedial action schemes. And I've got time for one more here. Another application, load shed. In fact, load shed, I'm going to say here, this was done initially inside of an industrial facility, but the extension to the wide area utility is automatic. Because now with this ratable goose will find its way throughout the larger utility infrastructure and be able to send in real time load shed information. In fact, one of the things I'm proponing is the concept of surgical load shed. Today, we cut off an entire, if we have a remedial action, we cut off an entire leg. So instead of cutting off the entire leg, what if we just incise the part that has to be removed to survive a particular remedial action? And this is now available. Back in my utility days, I was involved with a demand-side management program, and we were able to shed 5 kW inside an all-electric home by invoking critical peak pricing. Today, and now the critical peak pricing took part over a 1 hour period. So 1 hour before, we would schedule, and then literally at the hour, all the loads would turn themselves off. What are the loads? You go inside of a home, electric hot water. I can turn off your electric hot water heater and you wouldn't know the difference. I could change the temperature of how you cool your house. You wouldn't know the difference. I could suspend your dryer, the heater on your dryer, and you wouldn't know the difference. These are all surgically sheddable loads that exist inside the home today. We now have a mechanism to get access to these elements inside the home. Again, I call them surgical load shed instead of turning everything off. On large industrial sites today, many of these industrials have on-site gas turbines. Gas turbines are highly efficient today. The high-end devices are hitting 61% efficiency of the burn cycle of natural gas, which is just, compared to a coal power, I mean, even a nuclear plant only hits like 40% efficiency. These are hitting 61% efficiency. So we're seeing a lot more of these. Yeah?
Mark, you're talking about combined cycles.
Yes, combined cycle plants are hitting, the combined cycle plants are hitting 61%. Regular not, yeah. They're more like 40 then. So what's happening in these plants, depending upon the mix of generation to load, the goal is for the plant to survive a utility event, because all of these plants will typically have a utility feed as well as the internal generation. I was involved with one plant where 3 different times they lost the utility feed and only had 1 generator up and running. And lo and behold, 1 generator, no utility, the entire plant crashes. The cost of that crash is horrendous. A lot of these plants have steam heated processes, and when you quickly cool down that steam, you get cracks in all of their boiler tubes. Very, very costly to repair, and weeks of downtime in repairing those failures. So it's very logical to implement load shed on this localized basis. And again, you can read the text. I don't put read text for you there. But in general, we can create a model, and the model looks at internal generation, external feeds, and internal loads. The sum of all of these has to always be 0. So loss of any one of these, or where the sum is no longer 0, forces a scenario where we have to either, well, typically we're going to shed load in order to maintain stability inside these industrial facilities. This is an actual scenario from an industrial. This particular industrial has 2 internal gas turbines, each one at 47 MVA, and it has 2 feeds coming in from 230 kV feeds coming in to 2 transformers. Any single transformer can run the entire plant, but guess what's happened 3 times? as I mentioned, they've lost the two 230 feeds, and they had 1 unit out for repair. The probabilities are small, but it's happened, and it's cost this plant literally multiple millions of dollars. So, bottom line is, it's possible today to detect these outages, and when you detect these 3 breakers being out, as an example, this is an immediate trigger for load shed. Thank you. The paper, the presentation goes into details on how this was actually implemented. I won't go into too much detail here. But the takeaway is there was a main control house, and then there were 2 remote substations, and you see the one's about 3,000 feet away, and the other's about 1,400 feet away. What's the logical solution to shed load messaging? Goose, all right. So this is exactly what was done. So Goose messaging was established to send trip messages to the 2 remote substations. Now, observation. You see 3,000 feet. Over standard Ethernet, this is no problem at all. Standard Ethernet is good for 2 kilometers. This is standard multi-mode Ethernet. So using standard Ethernet was very, very easy to send a message over fiber optic. This is over fiber, by the way, just to clarify. Over fiber. Over copper, forget it. Doesn't work over copper. But over fiber, I can do 2 kilometers on standard Ethernet. By going to a laser Ethernet, I can get easily up to 4 kilometers, and then by going to single mode, I can go up to 100 kilometers. And we actually have done one project in Brazil where we went across the Brazilian rainforest with fiber on a remedial action scheme, and that was actually 200 kilometers. Required some special amplification equipment. Anyway, this was set up, and in each of these, there were Ethernet switches that were installed that connected to multiple relays inside these remote substations that were connected to actually trip the loads dynamically. Some details here. I will talk, did anyone talk about PRP at all?
Yes,
You did?
I mentioned it.
Mentioned it.
I had time only to mention it.
I will mention it again. In this diagram here, you see 2 Ethernet switches. It turns out that relays are much more reliable than Ethernet switches. And you have one Ethernet switch where everything is put together at one point, and that one Ethernet switch fails, you've taken your whole scheme out of service. So in the first implementations of 6150, there were multiple Ethernet switches installed, and messaging went up either one switch or the other. If the one switch failed, the message would have to be rerouted to the alternate switch. This used a protocol called Rapid Spanning Tree, or RSTP, Rapid Spanning Tree Protocol. It works. Problem is performance. It may take as much as a half second to switch.
I talked about it.
Okay. So going forward, this is old now. This was done with Rapid Spanning Tree. Going forward, I would do this again. I would use the parallel redundancy, where I have 2 paths going up simultaneously. But it is an important part of a design of these
And
systems.
I mentioned HSR as well.
All right, so this customer was very, very brave. They actually let me, they let me island the plant twice. They were very brave. I didn't let them down, but I came pretty close, actually. We did it under 2 scenarios. One where there was an overpower in the island, meaning that the plant was operating on comeback. It was only drawing 27 megawatts, and the generators were pumping out 37 megawatts. So when you island the plant, what do the generators got to do? They got to very quickly slow down. The engineer I worked with on the plant was very progressive, and they agreed to put in synchro phasers in the plant. So we actually captured the dynamic response of the generator using synchro phasers. And what you're looking at here is the synchro phaser angle response of an unbalanced island. So when the island was, we separated from the main utility with 10 megawatts of excess generation. What's the generator going to do? Well, you're looking at the angle of the generator here, and starting at this red line here, you see the angle starting to increase. This is the angle as measured by the synchro phaser at the plant. And this angle increased for about 1.78 seconds. And then what do you see at 1.78 seconds? It peaks out. The angle stops increasing and starts to decrease. Now, I'm not going to go into synchro phases here, but suffice to say, the increasing angle means the generator is accelerating. The decreasing angle means that the generator is slowing down. And so what we see here is the actual dynamic response of the machine. In fact, I can now, knowing this information, I can actually compute the inertia of this entire plant. Because I know, what do I know? I know d omega dt, the change in speed over time. I know what the mechanical torque was, and I know what the electrical torque was when I instituted the island. I can calculate the inertia of the entire facility using this technique. Let's see. If there's more interest, there's a whole paper on this. Bottom line is, in the test we ran, from initiation of the island at time 0 until the load shed message was received at all the remotes was 10 milliseconds. Of that 10 milliseconds, 8 milliseconds was debounce time on the digital input from the breaker auxiliary contacts in the yard. So the actual time to make the calculation, 2 milliseconds. Yeah.
So the deceleration is due to the load shedding,
Yes. Well,
not due to the governor response.
no, and that's a good question. The deceleration, there was no load shed on acceleration, so I do not shed load on an unbalanced island. The governor response slowed down the generators. I have a second case I didn't go into detail on where it was caused, where the deceleration was abated by shedding load. So we actually did that case also, but I just didn't go over it here in detail. Question?
So your plot was showing the governor response,
Yes.
not load shedding.
Correct.
Right.
There's a second plot though. The second plot I didn't go into detail on, and it does show the load shed response. And I think that's about where we're going to go today. All right. Your show, Wendy.